Dolek.
Okay, so thank you all for coming. We're happy to have Ronnie Kamai from Ben-Gurion University. So Ronnie did her bachelor's and master's in geology in Ben-Gurion University, and then continued to PhD in UC Davis, where she worked, among other things, on liquefaction. Then she did her post in the Pacific Earthquake Engineering Research Center with UC Berkeley. And ever since, she's working on everything related to earthquake hazard mitigation and ground motions. She's at BGU since 2013, and today she's going to summarize a lot of what she's done in previous years. Thank you.
Thank you, Tzachi. Hi, nice to be here in a full room too. So, hello everyone. So I usually start a talk about seismic hazards with you. I can't start a talk on seismic hazards without showing some pictures of previous disasters, just to kind of tune us into why we're even here or why we care about this topic and all the details that we're going to talk about in the coming hour or 40 minutes. And these are just, a sample of pictures from previous disasters throughout the world, some more classical, some more recent. All of these, of course, caused enormous damage, both economical and loss of life, and injured, and people have lost their homes. This just a year ago in Turkey. And in our own neighborhood, of course, we have a catalog, an extensive catalog of historical records and archaeological evidence showing us that earthquakes, big, damaging earthquakes, are not foreign to us in Israel either. So they have happened in the history. And when we look back in all the different historical and archaeological sites, we can see that we had a damaging of a significant earthquake approximately every 100 years here in our region. And the most recent one was about 100 years ago with the epicenter located north of the Dead Sea, around Jericho, causing damage. Of course, 100 years ago, the population here was much, much more sparse, so the number of dead was relatively not enormous like in Turkey, for example, last year. But if we interpolate or extrapolate to the number of population today, we understand that the hazard is significant. And this is a picture from not very far from here. You probably know exactly where this is from, right? Mount Olives. So even in Jerusalem, of course, extensive damage. And really what I'm coming from the engineering point of view, and mainly what we're trying to ask ourselves is, we cannot prevent these from happening. This is the forces of nature are way above our ability to control, but the only thing that we can do is be more prepared, right? So from the engineering standpoint, we're trying to ask ourselves, what are we going to do to be more prepared? And, before the slide that I was going to talk about, so from the historical and archaeological records to the more recent recorded catalog. So we have also a seismological catalog or an event catalog of recorded earthquakes. And we can see big clusters of earthquakes, but mostly we can see that the larger and more significant earthquakes, even though this catalog has, the blue here are magnitude 5, so they're not very significant, but they align along very well mapped and familiar fault traces. So we know that our main seismic source in our region is an active plate boundary along our eastern border, right where the relative movement, and we should all be familiar with that. And we see that in the seismic catalog. So we have a long-term archaeological evidence, we have the short-term seismological evidence, which is really barely 100 years of recorded earthquakes. Really, so we want to ask ourselves, what do we do to be more prepared? And we need to remind ourselves that earthquakes don't kill people, buildings do, or structures do. And for that, again, from the engineering standpoint, we want to build our structures to be safe, to withstand an earthquake, to be able to get that load and still stay standing and not kill anyone. So really what we're after is a design ground motion. We want to be able to estimate the ground motion at a specific site, let's say here, from a future earthquake. But what is this future earthquake? Where is it going to happen? When is it going to happen? How big is it going to be? These are many questions that if I had answers to, it would have been easier to estimate the ground motion, but I don't really know exactly where the future earthquake is going to be along that long Dead Sea transform. I don't know when it's going to happen. I can only assign probabilities to all of these. I can say, I had a large earthquake approximately every 100 years in the past, so I have a rate of occurrence of these earthquakes. I know that the location, this earthquake should happen anywhere along that transform, so I can again assign probabilities. I can say, it could be here, it could be here, it could be here. And even related to magnitudes, I can assign what is the probability that this future earthquake is going to be small versus intermediate versus large. And of course, we have different probabilities. It's more common to have very small earthquakes. And as we talk about larger magnitudes, the probability decreases. So we have some sort of probability density function which helps us estimate what magnitude it's going to be. And all of these lead us to use a probabilistic framework. So the way most of seismic hazard analysis is done worldwide, not all, there's a small percentage that still does deterministic, but today we're going to talk about the probabilistic seismic hazard analysis platform. And really what it is it's a platform to, again, estimate what is the ground motion from a future earthquake. And what I need to do within this framework is, first of all, build a seismotectonic model. So look around me and define the main or all of the seismic sources, locate them so give them coordinates, know where they are, what's the geometry, what's the length, what the dip, strike, where is the seismic source? Am I going to represent it as a line or a plane or an aerial source? So I need to define those. Each of these sources, I need to assign an activity rate. I need to define how active is this source. So for example, on the Dead Sea transform, I can measure slip rates with GPS. I can measure slip rates with geological features. I can measure slip rates or seismological activity. I have different tools to estimate the activity. With less active faults, like for example the Carmel fault, there's a greater uncertainty. I know that it's probably active. There's also debate about that. But I need to assign some sort of activity level to this fault, and also a relation between small and large earthquakes on this specific fault. What am I expecting to get? And after I define my seismotectonic model, I also need to use some components to compute what is the actual ground motion going to be at my site from a future earthquake. So how am I going to compute the resulting whatever ground motion parameter I want to use, let's say PGA, here as a function of distance, magnitude, and a bunch of other parameters. And eventually what I do is I compute this thing for all of the possible scenarios. So small magnitudes, large magnitudes, on this source, on this source, on this source, on this source, all of my possibilities. I assign a probability. So what is the chance that this specific event is going to happen, and give me a 0.1 G PGA at my site? What is the chance that a different earthquake is going to happen? So I assign probabilities to all of these different scenarios. And eventually what I do is I sum them up, because it can be either this or that or that or that. So I sum up the probabilities and I get a hazard curve. And the hazard curve gives me what is the probability of exceeding a certain degree of ground motion level. So again, what is the probability of getting 0.1 G or larger? What is the probability of getting 0.2 G or larger? Okay? So this is what the hazard curve looks like on a linear scale. And then I'm done with the seismic hazard analysis, but now we go to the decision makers, the government, the regulator. Someone needs to choose. So now that we have all these probabilities, how do we design? What do we design for? So a decision maker needs to choose what level of hazard we are going to plan for. And typically, ordinary structure, and when I say typically, it's worldwide, but this is from the Israeli code, and I'm going to keep referring to it, so remember that it's called IES 413. So this is what the current Israeli code 413 for building code for preparedness of earthquakes, so how to design a structure against earthquake loads. These are the loads that we get from the code for ordinary structures. So the hazard level is probably hard to see, but it's 10% in 50 years. And that deals with some Poisson probability, but basically what this corresponds to is we assume that we're going to get this ground motion every 500 years. So this is the load level or the acceleration that my site is expected to see every 500 years. And if I want to design a more sensitive structure like a bridge or a hospital or a power plant, I will look at longer return periods, and that would give me higher ground motions. So I can look at 5% in 50 years or 2% in 50 years, which gives me about 2,500 return period. And you can see that maybe you can see, but the numbers here are much higher. So this is what we have today in the Israeli building code as the hazard, as the numbers that the engineer needs to take and put into the structural analysis. And what I want to talk about today is different studies that we've been conducting in my group and with collaboration with other colleagues, of course, mostly from Israel, trying to challenge these many assumptions and many models and components that lead us to compute these levels. So trying to look at the different components that are part of this, creating this hazard map and challenging the assumptions that it's based on. So when we talk about ground motions, we usually talk about it as a compilation of 3 components. And this also corresponds to the PSHA framework that I talked about before. It kind of, it's just a different figure. But we talk about a compilation of source, path, and site effects. So I need to define the source. I need to define the path function, which is basically how are the waves going to propagate from the source to my site and what is going to happen to these waves on the way. And then what is the actual site? How is the actual site going to affect my ground motions? So what I'm going to do in the time that we have left is kind of skim through different studies, not going to go into very much detail on each one of them, but kind of touch on different studies related to source, path, and site that we did, of course, very specifically in Israel, and trying to look at different approaches of modeling these components. So let's start with the source. So again, the source representation means I need to build a seismotectonic model that represents all the seismic sources in the area that can affect me. So this is the seismic model, seismotectonic model that is today used in the current building code 413, and it is based on work by Gadi Shamir in 2001, and then following work by Avi Shapira and Rami Hofstetter, who assigned activity rates. So what we see here is that what they did is they divided our region into polygons, discrete polygons. Each one of these polygons has a uniform activity rate, so one number of activity rate, and the earthquakes can pretty much happen anywhere uniformly within this polygon. And then there are a few, before the problems, the activity rates are based on the seismic catalog. So like we said, the seismic catalog or the event catalog is pretty limited. It's only recorded earthquake. It gives us earthquakes, gives us 100 years back, but really it's complete since let's say 1980. So it's a very, very short time window, and we can't it's not necessarily correct to assume that the activity rates that we see in 20 or 30 years are representative of a much, much larger time window, longer time window. So the activity rates are based on the seismic catalog. And then another problem with this type of model is that all of these zones outside of the polygons get a zero activity. So there's a zero chance of an earthquake occurring anywhere outside this polygon. And we know that in probabilistic frameworks, it's very bad to give anything a zero chance, because there's a very, very slight chance of very surprising things that can happen in earthquake land. So a zero chance is not a great thing. And then the uniform, and mainly, really the activity rates that we assign these polygons along the transform don't really match the activity rates or the slip rates that we measure with other tools or with other approaches. So what we suggested, and it's not really us suggesting, it's really looking at the state of the art everywhere else in the world. What's common to do is represent a very well-characterized, mapped, long fault like we have in the Dead Sea Fault System as planar fault. So there's a fault plane. The rupture will happen on that plane. It can't happen randomly in the area. And it has to happen along this plane, and then we can give this plane a slip rate which matches both the geological evidence and the geodetic evidence and everything that we can bring in. And then we're left with the questions, okay, so what do we do everywhere else? So everywhere that is not on the main fault that can be mapped, we can assign a continuous grid of seismicity. So we run a kernel across the entire region that we decide is significant. And this kernel computes activity rates in every grid cell, smoothes them, and we have a continuous function of activity everywhere except for the main faults. And then we can discuss, okay, so how do we want these two different layers to interact with each other? How do we make sure that we don't double count the slip rate on the main faults and the background activity? And there are different approaches for that. I won't get into the details. If you want to hear them, you're more than welcome to ask me later. So we have two different approaches of how to interact between the fault planes and the background smooth seismicity. And then we compute hazard. So we compute hazard for the entire country with all these different approaches. So model 1 is the current model in SI 413. And then all these other alternatives are different combinations of the kernel, and do we do it fixed size or an adaptive size. And instead of showing you maps, which are much harder to compare colors between, we're going to look at 6 specific locations. So we have Tiberias, Haifa, Jerusalem, Tel Aviv, Beersheba, and Eilat, which, except for being known points on the map, they also represent very different points in terms of hazard. So the hazard in Tiberias is going to be high because it's right on top of the Dead Sea Fault System. Same thing with Eilat. Tel Aviv is going to have a much lower hazard. So we're kind of looking at different places in Israel also in terms of hazard. And then we compute the hazard for all these different points with all these different models and look at, does it even matter? So 2 things that I want to, okay, let me first explain what we are seeing. So on the left is PGA, peak ground acceleration. It's one ground motion intensity measure. I can look at others at a hazard level of 10% in 50 years. And on the right is PGA at 2% in 50 years. So those are 2 different points on my hazard curve. One at a return period of 500 years. This is at a return period of 2,500 years. And these are my 6 locations: Tiberias, Haifa, Tel Aviv, Jerusalem, Beersheba, and Eilat. And the gray dot is the current building code, model 1, and all the other colors are our alternative models. And I don't want to specifically talk about which one of these alternatives is better, but what I want you to note is that in almost all of the cases, the current model is underestimating the hazard. It's significantly lower than all the other alternatives, and that the seismotectonic model matters. It can really change the hazard that we are predicting, And again, I want to emphasize that all these different approaches, we can debate between specifically what type of slipper we want to put in the fault, but these represent the state of the art better than the current gray dots. And I'm happy to say that the GSI has been working on updating the seismotectonic model in the code for a few years. And this is an ongoing project, and I think very, very soon to be mature and out there. So, which of course is going to be much more similar to these colorful dots than the gray dot. So this was an example of a study on source characterization and how that really matters to the hazard results. And let me give you a different example on another very long-term, maybe 5 years, I think, project that I did together with Gonia Godabiran from the GSI on path. So when I say path, really what I mean is, again, given an earthquake scenario, if whatever scenario, let's say a magnitude 6 with a location, I don't know, south of the Kinneret, what am I going to feel at different locations in Israel? So I need some model, some formulation, some equation to tell me what am I expecting to get at a distance from a specific magnitude and all the different characteristics. And really there are two main approaches, again in the seismic hazard community, to predict this level of ground motion. So I can talk about physics-based approach and conduct a very, very demanding 3D simulation of finite elements with wave propagation and everything, and we do that, but it's very hard to do an entire hazard analysis with these tools. It requires a crazy computational effort and has other limitations, which I'm not going to get into. The more popular, simple, but popular approach, definitely in the engineering world, is to use an empirical approach. So we gather a lot of data, and today we have really a very abundant data of ground motion records, and we look at, basically we ask, how did these or what type of ground motions did we get from all these different earthquakes in the past? And of course, we all know as geologists that the past is the key to the present or the future, or so we are we're basing or relying on what we understand from these past earthquakes in our prediction for a future earthquake. So these components used to be called attenuation relationships, and if we look at models from the 90s, we see that they were very, very simple function of magnitude and distance. But as we have more data and more computational resources, more of these models are coming out yearly, and of course they're becoming much, much more complex with many, many parameters that we are trying to characterize the source, path, and site components. We call them today GMPE, so ground motion prediction equation, or ground motion model. We're trying to call them MOTEC in Hebrew, Model Tnudot Karka, so please use that term. But this is the component that I call path. So I'm computing what is the expected ground motion from a future earthquake. And if I look at, so the common practice when I do a hazard analysis, let's say in Israel, and I don't have a local GMP, I go to all the different GMPs worldwide and I choose some GMPs that are supposed to represent my conditions here, and I would go to GMPs from an active crustal region, not a subduction, not a stable continental region. But even then, I look at a very, very wide range of models. So these are all models, again, kind of hard to see the font, but the very, very light blue is Campbell-Bazorgnia 08. This is a model that was published in 2008, and this is what's today used in the current building code. All the other blue colors are successors of the 08 models. There are 2014 models, and they are mostly based on, so they use the same researchers or engineers developed the models on a much, much more extensive database. The green models are from Eastern US, and the red and pink models are from Europe. So we see that the models are different based on different databases, regional effects, different constraints that you put on a model when the framework. And our objective coming into this project was to create a model that is based on local data for Israel, that it's engineering oriented, meaning it needs to be in terms of some parameters that engineers like to use. So PGA is not enough. Engineers look at ground motions in terms of spectra, and specifically response spectra. Again, I won't go into the details of how that's computed, but it's a way to look at ground motions, and it's in spectral ordinates. So we want to be able to create our model in terms that engineers can actually use. And we also want it to be based on local knowledge. And we also wanted to capture the epistemic uncertainty, so our uncertainty in different model forms, parameters, right? Because we don't have enough data to really know what our model needs to look like. So we need to make some assumptions, and hence we have uncertainty. If we look at, so the first step we did in this project was to develop a ground motion database. So the ground motions were available in the geophysical survey, now in the geological survey, but they weren't really available, again, in engineering terms. So we needed to compile the station database with all the different parameters that we need. The event database, we have 300 events, about 90 stations when this came out. And we do a uniform processing to all the different ground motions and end up with about 3,000 records, which have 2 different horizontal components. We compute the average. We do all this uniform processing. And this is what our empirical database looks like. This is magnitude and this is distance. And probably hard to see the numbers, but this is 100 kilometers. So really we have a lot of small earthquakes at a range of distances, but we don't have very many earthquakes that we care about, because we really want to compute the hazard for magnitudes 5 and up. We don't care about magnitude 3s in the engineering world. And we don't have those. Those are almost non-existent in the empirical database. So for that, what we did here is we actually took what you could call a hybrid approach. So we take 5 different databases. One of them is the empirical database, as it is, but we also create 4 different simulation databases, more simple simulation, not a huge 3D wave propagation, which is calibrated to local effects. And we create 5 different databases. We use 2 different host models. So basically we take a global existing GMPE and we adapt it, and we only regress specific components. So for example, the coefficient that talks about large magnitude scaling, I can't constrain because my data doesn't allow me to constrain it, or other components. So I only constrain what my data actually lets me, I have enough data to do. So I have 2 host models, 5 different databases, and I end up with 10 alternative GMPs in terms of Fourier amplitude spectra. So I have 10 different GMPs in terms of Fourier amplitude spectra for a bunch of reasons, and then I do an entire process of actually transferring it into the more engineering acceptable response spectra through another computational step. So this is what my Fourier spectra models look like. This is the distance scaling. So I have here a ground motion parameter. This is the Fourier spectra at 5 hertz as a function of distance. This is 9 because we had to let go of one of the models, so I have 9. So these are my 9 different models, and this is how they scale with magnitude. And you can see that we have, a range. We have a range of results as expected. This is what we wanted to do. We wanted to be able to capture the epistemic uncertainty. And now, in order to move into response spectral domain and also add into my model components that are really, really important when I try to compute hazard from a large future earthquake, but I don't have enough information to constrain it from my local data. For example, like hanging wall effects. I don't have any information about hanging wall effects in Israel because we didn't have enough large recorded earthquakes, but I know it's important in future earthquakes. So I bring that in from an existing model. I bring in nonlinear site response from existing models. So again, it's kind of I don't know, building up the model using both available data and constraints from outside. We take the mean and standard deviation of our 10 or 9 alternative FAS model, Fourier amplitude spectrum models, and convert them into response spectra using RVT, and compute our final engineering-oriented model. So we have the model called KYB, Kamai Agoda Biran, in black, and the other global models, just for comparison, in the different colors. And you can see again, this is at short spectral period, this is a long spectral period at a distance of 10 kilometers from the fault, 100 kilometers from the fault. And you can see that the model has the same shape as the other global models. Sometimes it's higher, sometimes it's lower. This is what the data showed us. We didn't try to get right in the middle because I can just compute an average if I really want the middle. So this is what our model looks like with magnitude scaling. This is what it looks like with distance scaling. So again, magnitude 5, magnitude 7 at 2 different spectral periods. And sometimes we're high, sometimes we're low. But this is, this is what we get. And of course, when we want, the final question is, does it even matter? So we run the hazard again for the entire country. Look at our 6 different, so these are the different maps with different combinations. The other thing I should mention here is that we run, we run CB08, which is today in the building code. We run CB14, which is Campbell and Vizorgnia, but their updated model from 2014. It should be more, updated than 08. We run the BB is backbone. So backbone means we run the model with a lower and upper bound, which kind of gives us a range of epistemic uncertainty. And then this is an average of all the different models that came out in 2014 from the NGA West 2 project. And this is our model KYB22 and KYB22 with the backbone. So we run 6 different combinations of GMPs or ground motion models. And again, look at our 6 different locations throughout Israel. And here's what we see. So the black square is the current model in the code CB08. The blues are mostly based on NGA West 2, so a very big popular project which was released in 2014. And the pink symbols are our models with different combinations. And it's hard to say, there isn't really one model that's always high, one model that's always low. We do see that choosing the GMP can make a big difference. So here we're jumping from 0.5 to almost 0.8 in G. This is a huge jump in hazard in the structural demand. So the only, conclusion I want to take from this slide is the ground motion model matters. We need to think which one makes sense. How do we combine them? Do we take an average of existing models? Do we take, I'm not necessarily saying take our model for computing the code because it's kind of new and fresh, and sometimes we want to give these models time to be more acceptable in the community. But it matters, and we need to do these studies and try to come up with the best approach for choosing what is a GMP that's going to be used when we compute hazard on a national scale. So that's it for the path. And before I go into site response, what's my time frame?
Go on because we also just started a few minutes after, so.
Oh, okay.
Go on.
And can we turn on the AC? Because I'm dying here. Thank you. Maybe if I talk slower. So the last component that is in our convolution of source, path, and site effects is the site response. And site response is really, I need an entire talk or maybe 10 different talks to talk about site response. It's very hard to talk about it in 20 minutes, but I am going to try and give you just a taste of what that means and what we've been doing, but really there's a lot to say. So again, I can't talk about site response without giving the very, very classical example of the Mexico City earthquake in 1985. The earthquake happened right here on the shores of the Pacific Ocean. Mexico City itself is somewhere over here. It looks close, but it's more than 300 kilometers away. So it's theoretically, if we look at GMPs, we really shouldn't get much damage at a distance of 300 kilometers away. But here we see that Mexico City suffered a disaster with more than 10,000 dead, injured, homeless, economical loss. So really a huge effect on the city. And the more surprising or I don't know, anecdotal thing in this whole thing is that in 2017, on the same date, September 19th, there was another big earthquake that hit Mexico City. And in 2022, on September 19th, I don't know, but really, truly, another big earthquake that hit Mexico City. But really, the one that made the big damage was the 1985. And these are more pictures of the damage from there. And to try and explain it, again, very, very briefly, we're comparing between two seismic stations. So we have a seismic station called UNAM, which is sitting on the hills that surround the city. And we have another seismic station which is called SCT, and it sits on top of 40 meters of sediment, very, very soft lake sediments, which were deposited there before the city, of course, was built. And we compare the records, the ground motions recorded at UNAM and SCT, and this is what it looks like in time domain. So this is what we get on rock, and this is what we get on soil. So you see the huge amplification just by the waves propagating through the soft soils. And we also see that in spectral domain. So this is spectral acceleration as a function of spectral period. And you see that this crazy amplification happens mostly at very specific periods or frequencies. So it's also very sensitive to the depth of the sediment and specific frequencies. And here we have an 8-fold amplification. So it's seriously very significant. And of course, we have to account for that somehow in our hazard computations. So I go back to the code, and we check how is that accounted for today. So basically, in very, very simple terms, what the code tells us to do is this map is, again, a compilation of many, many studies conducted by Zorg Wirtzman and Yuli Zaslavsky. And what they say in simple terms is the green is rock, so don't worry about it. The black is very shallow profile, so the rock is close to the surface. You need to do a site-specific analysis, so really get your entire soil profile. The pinks are deep basins, but everywhere that there's white, just go to this table. This table gives you a site classification, A, B, C, D, E, as a function of the average shear wave velocity of the different layers. And another table gives you amplification factors. These amplification factors are based on work done in California in 1993 following the Loma Prieta earthquake in 1989, based on maybe, I don't know, 20, 30 observations. And this is what's in the code today. So obviously we said, again with Goni, we need to check. Let's see if maybe the amplification in Israel looks differently. Why do we need to take the exact same factors as they are since the 90s in the US code? Let's try to have our own work. So what we start with, I'll come back to this. What we start with is search for velocity profiles. At the time, we were able to compile 1,600 different velocity profiles, most of them from a method that, I won't go into from different methods. And velocity profiles meaning, what is the shear wave velocity with depth within my site up to a certain depth? The shear wave velocity is really an indication of stiffness. So stiffer sites will have a higher shear wave velocity, softer sites will have a lower shear wave velocity, and the amplification is a function of the stiffness and hence also the shear wave velocity. And when we take all of our profiles and just compute the average. So the average with depth, and we separate them into 4 bins. So this is all the profiles that their average is about 270. That's one of the classes here in this. We basically look at class B, C, D, and E. And we see the average profile in California and the average profile in Israel, California in blue, Israel in red, are different. So the velocity gradient with depth is different. So obviously we're expecting it to get a different site response. Maybe, some different, it can be higher, it can be lower, but we want to check what it is. So at the time when Almog Baram was doing his PhD work, we almost didn't have any recordings, and we had to compute the amplification ourselves. So we first defined what our rock profile looks like, and then we computed the amplification from each of our soil profiles with respect to this reference rock. So we also always have one reference point, and looked at the scaling of the amplification as function of VS30 for different spectral periods. And then we compare our scaling. So this is for PGA. Our scaling is in a continuous line. The reference rock is 1100, so this is the red line. And then the factors in the code today, the amplification factors in the code today, are these horizontal lines. So for every class, I multiply by, in this case, 1.6, okay, for class D. So you can see that in some places it's exactly the same, and in some places it's much, much lower. Obviously, it's better to have a continuous function of amplification as function of this site parameter. Another thing that we did with Almog, which was very significant, was also introduce a second parameter, which is not just the average velocity of the site, but also the peak frequency in which we get amplification. So you see this shape of the function is a function also of this F peak, and the F peak is a function of the depth of the sediments, the depth of the profile. And we have a continuous function of both of these. There's many more figures which I didn't put in today. We have an ongoing project now, which is looking at this slightly differently. We're compiling a different, not a larger, a different velocity profile database, this time for more shallow measurements. So we want to look at the more shallow profile. And actually, we do some measurements ourselves. We had many colleagues share data with us, both from industry and government, which was great. And the idea is to eventually create a continuous map of VS30 throughout Israel, which will be very, very applicable and useful for engineers, and also compute a bunch of other parameters. So if I want to sum up this very lengthy and kind of varied talk on seismic hazards, I would say that our current code requires updates and improvements, obviously, in all 3 components, source, path, and site, and we're working on it. The GSI is working on it, and I hope we'll have this soon enough. The current code is based on very many assumptions, which should be challenged. And hopefully today we have enough data, both from TRUA and from subsurface investigation, that we can actually develop local models and incorporate them into the code. I do want to remind us that there are still many, many pre-code structures that haven't been improved regardless of the current code. They don't even stand by the current code. So those are the first one we need to treat and improve and retrofit. I don't have a thank you slide, but thank you. Thanks for coming.
Thanks. Questions?
I think in the last slide of the path section you showed us, you showed for a very large spread of results between
yeah.
models, and you said how much it is significant.
This one.
But for other places, there's almost no spread. So does it have some physical reason from the model or from the specific site? Or
So it's a great question. We really need to go into each one of these locations. So for example, Be'er Sheva is relatively far from the main sources, so the near fault effects are less significant, and the average. I should say that even the models that say backbone, so the blue circle and the star, they're the average of the backbone. When I really want to do a seismic hazard analysis for a very sensitive facility, I run all these different hazard curves and all these different combinations of GMPs, but I don't only look at the average. I look at also at the spread of results, and I look at, let's say, standard deviations or whatever it is, and we don't see that here. We just look at the average result considering everything, but then still, this is what's going to go into the map. And you're right, some places I would say Tiberias, which is very close to the fault, and Eilat, which is very close to the fault, are more sensitive, and Tel Aviv and Be'er Sheva are less sensitive. But yeah, we need to go and look specifically at these locations.
So continue on that. Why is your Haifa prediction so low?
With the pink model.
Yeah. It's good.
Why is the Haifa prediction low? So I don't have an answer right straight up to specific. So I would go and again look at the hazard curve and look at what's driving the hazard. What type of event? So for example, I can show you here. You can see that for, let's say, compare these two slides. So this is short periods, magnitude 5 and a magnitude 7. For magnitude 5, close in, which is probably the event that's driving Haifa. So Haifa, we're not, the hazard, we can deaggregate the hazard and look at the scenarios that are mainly contributing to the hazard. So in Haifa, it's probably not a 7.5. It's probably more likely 5, 5.5. And you see that our model there is lower than the other global models. Whereas if I look at a magnitude 7, we're not that low anymore. Or if I look even at a magnitude 5 at a longer spectral period, we're even high. So this comes from the spectral shape and many different components that go into our databases. And even I would even take you back to our different simulation databases. These simulation databases, we use point source stochastic. So kind of a very simple computation, but it's calibrated to available data. But it's calibrated on data that we had until, so not a lot of data. And in the old, before Trua, we don't have a good constraint on high frequencies because of the velocity, because of the type of sensors. We don't have high frequency, high quality data in high frequency. So all of that comes together when I try to actually create a ground motion prediction equation. Our data, our ground motion catalog is not high quality. Today, I think that it's going to be different. We already have 6 years of Trua, so I think we're going to have much more high frequency data, and we can look if it looks a little bit different. But here, I remember that when we calibrated our simulations to the empirical data, the high frequency component was very low, and we had nothing to do with it.
But how about the source model? Is it the same source model that was in the other?
So this comparison uses one source model and the more updated one. So what was model 4 in the previous part of the source. So not the GSI model, but our most updated source model. But all of these use the same source model and just change the GMP. But so the difference is, we need to go back and see what's driving the hazard. What is the most dominant scenario? And then ask ourselves, oh, here, this model is low, this model is high. That's what's going to dominate, if that makes sense.
For the side effect chapter, isn't the geometry basing matter? So just the thickness of the cell?
Yes. So
I think we're basing what well-defined bases.
That's true, but in New Mexico, it's a very wide basin, so I think most of the effect is so when we talk about site response, I would say, I don't know, 80, maybe 90% of the literature and definitely of the engineering practice does a 1D approach. So the first order is that we say, okay, on a first order basis, we have an amplification with upward propagating waves. And of course, on top of that, we have local effects of basin shape and 3D effects and much more complications, which are, when it matters, they are considered, but mostly there isn't a good way to consider them today in practice. So for example, in the GMPEs and in the hazard code, in the hazard maps, 2D effects are not considered because we just don't have a way to include them in these large computations. They will, I think, in the future, but I don't know of any, simple engineering, practical model to account for 2D effects that's being used today widely.
Any other questions? So I have a question. At the beginning of the talk, you said that the hazard is underestimated with the current code.
With the source effects, yes.
Yeah, and you said that, maybe unrelated, but you said that the GMP used for the standard is the 2008, which you showed overestimates ground motions compared to other ones. So
no, it really depends. So CB08, it really depends. Again, it depends what you look at. So we look at a multidimensional space when we talk about ground motion models. There's a magnitude, the distance, the site, the mechanism, and the standard deviation. So there were a couple of figures where I showed CB08 was higher, but it's not always higher. It's not necessarily higher for large events, which we care about, and the standard deviation is much lower. So I would definitely not recommend using it in any future application. But here, all of these are computed with the same ground motion model. The only thing that changes is the source model. So these are all computed probably with either CB08 or CB14. So either the original one or the updated one. So the only difference here is the source model. So we're comparing apples to apples, trying to.
And did you get to compare VS30 with actual amplifications from earthquakes?
Yeah, of course. Yeah, so I can. Well,
VS30 and
simulations. Oh, in Israel, specifically in Israel. No. I'm trying to think. No. We need to define, when you compare, we want to look at a large database. You don't want to compare point to point because there are so many other variables. So you want to look at kind of more statistically, and then you need to, actually,
like a proof of concept, doing it and at a seismic station.
Just comparing to VS30?
We actually have ground motions to see if they are amplified compared to other stations. Like just do.
Oh, they're definitely amplified. They're definitely amplified, but I just don't know how they are with respect to the factors that are in the code. They're definitely amplified. I don't know by how much. I don't think we did a comparison of recent ground motions. And of course, we really only have a good database in the last few years. So before that, it wasn't really, most of our stations were on kind of rock or soft or hard soil conditions. Yeah.
Okay.
But yeah, we should. Thank you.
So let's thank Ronnie again. Because it's very loud outside, is it okay if we do the 60 seconds now?
What is the boss?
טוב, רוני אמרה לי שלא ישנה כל השבוע בגלל ה-60 שניות האלה. אז
רגע, אני צריכה לעבור לעברית? שנייה.
כן, אז צריכה לדבר בעברית, שיחה ברורה, שכולם כאן יבינו מה רצית לדבר בהרצאה שלה.
מה, אתה אומר שהם לא הבינו? רגע, לא, שנייה, אני צריכה לעשות סוויץ'.
תתחילי.
לדבר אליהם או אליך? אליהם. אהלן, שוב שלום, אני אדבר בעברית. אז מה שדיברתי עליו זה בעצם איך אנחנו מסתכלים על אנליזה של סיכונים סייסמיים, ואיך כשאנחנו מעריכים סיכונים סייסמיים זה מורכב משלושה קומפוננטים עיקריים, שלושה רכיבים, המקור, הדרך והאתר, ותיארתי מחקרים שאנחנו עושים פה ב10 שנים האחרונות, בשותפות עם קולגות מהמכון הגיאולוגי ואחרים, להסתכל או לאתגר הנחות שונות ומודלים שונים שאנחנו משתמשים בהם כשאנחנו מחשבים סיכונים סייסמיים בישראל, בפרקטיקה, בקוד וגם בתעשייה, ולהסתכל על המודלים השונים האלה וגישות אלטרנטיביות שאפשר לאמץ כדי לשפר את הערכות שיש לנו היום בקוד. ושיהיה לנו בהצלחה.
אוקיי.